So we're looking at how to find the inverse of a function algebraically today. Okay, and soon we'll focus on graphically how you find the inverse. We'll do a little bit of graphing though today. An inverse relation, that's where you interchange the input, and the input values, those are just x values, right? So we're interchanging the input and the output are y values of the original equation. That just pretty much means swap x and y. And whenever you do that, if you if you swap your input and output, then your domain and range are also going to be interchanged. So this is the domain and range. So basically what I'm saying, the domain of your original function will be the range of the inverse. Or the range of your original will be the domain of the inverse. Okay, so we're going to find an inverse relation for this function. Y equals 3x minus 5. So to find the inverse, you really just swap x and y. Okay, so we're going to swap x and y. We're going to swap x and y to get x equals 3y minus 5. And now we're going to solve for y. So if I have x equals 3y minus 5, what's my first step in solving for y? Say it. I'm going to add 5 to both sides. So x plus 5 equals 3y. Right, that came from adding 5 to both sides. And then the next step is going to be to divide everything by 3. Now, I could divide the entire left side by 3, but for our purposes, I'm going to write it like this, where I just divide each thing by 3. It means the same thing. So I have y equals 1/3 x plus 5 over 3. Okay, and I could have left this as x over 3. It's the same thing as 1/3 x. So this is the inverse of y equals 3x minus 5. Alright, so a few more examples. If we have y equals 1/2 x plus 2, and I'm going to find an inverse relation, my first step is to swap x and y. X equals 1/2 y plus 2. Solving for y, I subtract 2 from both sides. So x minus 2 equals 1/2 of y. Now, how do you get rid of a half? Yeah, I'm going to multiply everything by 2. Right? Because what's happening is you're actually dividing by a half. But whenever you divide by a fraction, you flip and multiply. So I'm going to multiply both sides by 2 to get this half to cancel. So now I have y equals, distribute the 2, 2x minus 4. Right, the next function is a squared function, so no longer just linear. I've got y equals x squared minus 3. So we start the same way. X equals y squared minus 3. Okay, I'm going to get this y squared by itself by adding 3 to both sides. So x plus 3 equals y squared. Now how do I get rid of the squared? I take the square root of each side, and what do I know about even roots? What do I have to remember to put in front of the square root of square root of x plus 3? Plus or minus. Because for even roots, we don't know what it could have started off as. So don't forget your plus or minus square root of x plus 3. Okay, for the next example, we have y is equal to negative 64 x cubed. So I'll swap my x and y. X equals negative 64 y cubed. So what do you think is going to be the first step of this problem? I can't cube root yet because I don't have that y. The y is the only thing being cubed, so I need to get that by itself first. So the first thing I need to do is divide by negative 64 because it's being multiplied by that y cubed. So I'm going to divide both sides by negative 64. So now I have x over negative 64 is equal to y cubed. Now that the y cubed is by itself, I can take the cube root of both sides. Because the cube root of y cubed, well, that's just y. Now, on the left side, cube root of x over negative 64, that's okay, but remember that if you're taking a cube root or a square root or whatever, that's the same thing as the cube root of the numerator divided by the cube root of the denominator. This is helpful to me because I can take the cube root of negative 64. Right? So since it's a cube root and it was negative, I know that it'll stay negative. And what's the cube root of negative 64? Negative 4. So we have y equals the cube root of x divided by negative 4. Okay, for D, I want to come up with an inverse relation, but I don't even know what the relation is first. So I'm going to have to write an equation based on this graph. So I look at it. Its parent function is linear because, well, it's a line. So for linear functions, I know I just need y equals mx plus b, right? So y equals mx plus b. Well, m is the slope, so to find the slope, it's rise over run. Well, let's look at it. Rise over run, I'm going down 1 over 1, down 1 over 1. So what's my slope? Negative 1, because it's going down. Right, so I just have negative 1x, so negative x. And b is the y-intercept. What's the y-intercept? Positive 2. So this is my original. So for my inverse relation, I'll swap x and y and solve for y. So subtract 2 from both sides. X minus 2 equals negative y. How do I get rid of that negative y? The negative in front of the y. Divide everything by negative 1, which really just changes the sign of everything. So negative x plus 2. Here's something interesting. Look, the original and the inverse are the same. Right? And we'll talk more about that later whenever we talk about it's because they're both reflecting over this one line, and sometimes a reflection can land right on itself again. So sometimes your inverse and the function will be the same thing. Inverse functions. So f and g are inverses of each other, so the functions f and g. If and only if f of g of x equals x and g of f of x equals x. Okay? So let's see what that means with an example. I'm going to use the functions f of x is equal to 3x minus 5. Now, I don't have to use a g of x. I can also use this thing that's f inverse. So this f to the negative 1 means f inverse. Okay? So f inverse of x is equal to 1/3 x plus 5/3. So I'm going to use composition of functions to verify that these two things are inverses. So I could say f of f inverse of x. Well, if we remember from our composition, that means that I'm going to plug all of f inverse, so all of this function, into the x of f. Right? So it's really just saying, okay, plug 1/3 x plus 5/3 into the x of this f function. So the f function is 3x minus 5, so 3 times all of that stuff minus 5. And all of that stuff was 1/3 x plus 5/3. Okay, so now I'm going to distribute this 3 to both things. 3 times 1/3, this is the same thing as saying 3 divided by 3, since that 3 is in the denominator. So it cancels, and I'm just left with an x. So this 3 times 5/3, the 3's cancel each other again, and what are you left with? A positive 5. And then on the outside, you still had a negative 5. So the 5's cancel each other, and you're left with x. So f of f inverse of x equals x. I also have to check that f inverse of f of x also equals x. So this time I'm going to take the f inverse, and what are you replacing the x's with? This other function, 3x minus 5. So I'm going to write out this whole f inverse function. 1/3. I like to just leave a blank wherever there's an x plus 5/3. And then I replace that x with the 3x minus 5. So a lot of times, I like to just skip this first step of writing it like this. And whatever the outside function is, I write that function down and I leave a blank where there's an x. Then whatever's on the inside, I take that function and put it inside those blanks. Okay, that's exactly what I just did. The outside function, 1/3 of something plus 5/3. And then you replace with the inside function 3x minus 5. So let's distribute 1/3 of 3x is just x. 1/3 times negative 5 is negative 5 over 3. I'm adding 5 over 3. These cancel. And I get x. So the compositions both ways equals x. So these two things are inverses of each other. So this is the horizontal line test. We can use it on our original functions to determine if the inverse is going to be a function. So in both of these examples, we have functions. Like this is a function, this is a cube function, this is a quadratic function. Right? So just the same way that you use the vertical line test on your original function to test if it's a function, we use the horizontal line test to see if its inverse will be a function. So this is a function, and its inverse is a function because the horizontal line doesn't hit it more than once. Here, this is x squared. This is a function, but its inverse is not a function because the horizontal line test hits the graph twice. And so let's play with that. We're going to use the graph of y equals negative 2x plus 4 to determine if the inverse is a function. Okay? So if the inverse is a function. Alright. So y equals 2x, negative 2x plus 4. How do I graph y equals negative 2x plus 4? Yeah, we start by plotting the y-intercept. It says a y-intercept of 4. So I plot that at 4. And what's the slope of this line? Negative 2. So my slope is negative 2. That means the same thing as negative 2 over 1. That way I can do my rise over run. So down 2 over 1, down 2 over 1, and so on. Up 2 and back 1, same thing. Alright, so I've graphed this function. Now I'm going to do my horizontal line test. Okay? Whenever I pass a horizontal line through this, is there ever a time that this horizontal line would hit the function more than once? No, so it passes the horizontal line test. That means that the inverse is a function. Alright, we're going to do it again, this time with a quadratic, y equals 2x squared. But notice that it's only for the x's that are less than or equal to 0. Okay? So this is a restriction on the domain. Okay, so that's a restriction on the domain. That means I only care about the x's that are less than or equal to 0. So normally whenever I would graph this, there's so many different ways I could go about this. I could figure out where the vertex is by doing opposite of b over 2a, but that's mostly for standard form. If I'm just looking at this, I'm going to think, okay, this is almost the parent function of just x squared, and it's been stretched by 2. The easiest way for me to find values is to just make a table. Okay? So typically our table would go from negative 2 to 2. I know. But our table isn't going to go from negative 2 to 2 because I only care about the x's that are less than or equal to 0. So I don't need this positive 1 or 2. Okay? Now, if you were to plug negative 2 into 2 times x squared, what's negative 2 squared? 4 times 2. So I've got the points. Negative 2, 8. Okay, negative 1 squared is, times 2 is 2. So negative 1, 2. Now I've got 0 squared is 0 times 2 is 0. Okay, and then my graph has to stop. So this is just the left side of a quadratic, right? That's been stretched by a factor of 2. That goes back all the way back to whenever we were talking about parent functions and transformations of them. So it's a skinnier graph because it's been stretched. So if we go back and we look at this quadratic, so yeah, if we go back and we look at this, we saw that this quadratic, the inverse is not a function because it ended up hitting on both sides. But now that we have the restriction of only going negative, if I do a horizontal line test, how many times can it possibly hit? Just once. So is the inverse a function? Yes. The inverse is a function. Alright, and that'll be all we're going to do today as far as like finding an inverse algebraically.